Here's how I defined the loss functions. You can see that these are pretty simple. That is, there's just one line of code really that we need to calculate for the real and fake adversarial losses. For my real MSE loss, or mean squared error loss, I'm comparing the discriminator logits d out with the real label 1. I'm squaring the difference here and then calculating the mean of that squared difference. And I'm making sure to just return that value. And I'm doing almost the exact same thing for the fake MSE loss function, only this time I'm comparing the logits to the value 0, and d out minus 0 is just d out, so I'm actually just squaring these logits and calculating the mean. Then I get to the cycle consistency loss. This takes in a real image, a reconstructed image, and a lambda weight term. So first, I'm calculating the absolute difference between the real and reconstructed image. This is a pixel-wise difference, and I just want one value that indicates the reconstruction loss. So I'll also calculate the mean of these reconstructed errors. This gives me my reconstruction loss. Finally, I'll multiply this reconstruction loss by the passed-in lambda weight value and return that. When we actually get to training, you should look at the original CycleGAN paper to see what value of lambda they used. In general, this will be an interesting value to play around with. I'd suggest starting at the value they use in the paper and just trying out lower and higher values to see what happens during training. Then, to complete my optimization strategy, I've defined 3 optimizers, one each attached to the parameters of my discriminators dx and dy, and one more attached to my concatenated generator parameters. And I'm just using the same hyperparameters as I did in the DC-GAN case, a low learning rate and a beta 1 equal to 0.5. Finally, we can move on to the training loop. I'll want you to complete this training loop, and so I'll present this exercise in the next video.